Okay, so maybe we can start. So thank you all for continuing with us for the second talk of the day. In this talk, we will have Denis Auroux from Harvard University, who is going to tell us about Fukaya categories of Landau-Ginzburg models and homological mirror symmetry. Thank you. The floor is yours.
Right. Thank you very much for the opportunity to speak in this conference. And thanks for coming, everyone. So I will try to give a survey of various recent developments around homological mirror symmetry outside of the Calabi-Yau case, centering on the symplectic geometry of what's now called Landau-Ginzburg models, but in the more basic mathematical sense, these are just symplectic fibrations over the complex plane. And so from a pure symplectic geometry viewpoint, the question is, how does one study Lagrangian submanifolds in a fibration over the complex plane or in a symplectic manifold relative to a divisor? So I want to explain basic things about these Fukaya categories and then talk about what this says about homological mirror symmetry in various classes of examples, and then try to explain and synthesize the two viewpoints in the language of spherical functors and try to explain some of the structural properties of the geometry that one sees. And so various parts of this talk are based on ideas that were first introduced to symplectic geometers by Paul Seidel, then by Mohamed Abu Zaid, and then further refined in the works of various people, including my students Ganatra, Sylvan, Hanlon, Jeffs. But there's actually other ways of presenting essentially the same picture in a different language. For the slightly conjectural ideas that I will explain are probably even more conjectural in some of those frameworks. So for example, you could substitute large chunks of symplectic geometry for microlocal sheaf theory using ideas of Nadler, the language of sectors of Ganatra, Pardon, Shende, work of Ben Gamage. Or further afield, there are completely different viewpoints on this. In math, from the work of Kontsevich, Seubelman, Kapranov, what's called the algebra of the infrared. And so the physics of this also originates in works of Hori and Vafa, Hori, Iqbal and Vafa, Gayotto, Moore and Witten, probably many other people. So the viewpoint I'll give on this is kind of pretty biased, and I would say what a traditional symplectic geometer would make of this rather than people from other backgrounds. All right, so with those preliminaries out of the way, what is a symplectic Landau-Ginzburg model for us? So it's just going to be a symplectic manifold in the real sense. I'm a real symplectic geometer. Okay, there's no holomorphic symplectic forms in this talk. Together with a map to the complex plane, whose fibers are symplectic submanifolds outside of some critical points. So there's a critical locus, but the smooth part of this map is a symplectic fibration. And almost all examples to date are actually Kähler quasi-projective varieties equipped with a holomorphic function. So you can perfectly just take that as your viewpoint if that's easier. So the goal of Fukaya categories is to understand Lagrangian submanifolds in a symplectic manifold and their intersection properties. And in the presence of a manifold with a fibration, the idea will be to probe the geometry of the total space Y in a way that sees the fibration, or at least its structure at infinity. And so the idea for that is to look at Lagrangian submanifolds of Y relative to, I would say, the fiber at plus infinity. So what you should imagine is that a Lagrangian submanifold will be of interest to us if it lives over a part of a complex plane that can escape to plus infinity, but not in other directions. Plus infinity is a choice of, it's just a convention, of course, but this is the basic idea of what we want to do. And why, I mean, this is pretty arbitrary, Well, one way to think about this is studying the geometry of pairs rather than just a space. You study a space relative to a subspace. For here, we are putting it at infinity. This is a bit strange. And of course, the big motivation that's not yet on this slide is that this appeared first, I think, in Kontsevich's idea of extending homological mirror symmetry to non-Calabi-Yau settings, to initially Fano varieties, for example. And of course, the physics literature also had similar ideas around the same time. I don't know the exact history of this. But quickly people came to the realization that the branes in the A model, which used to be just ordinary Lagrangian submanifolds in the compact Calabi-Yau case, would now need to have non-compact Lagrangians with this kind of prescribed behavior at infinity. So a basic fact of symplectic geometry is that in a fibration, all the smooth fibers are the same. This is very different from complex geometry. So, and the reason for this is that any kind of symplectic fibration has a preferred horizontal distribution, which is the orthogonal to the smooth fibers. And so you can use that gives you a preferred connection that you can use to transport points from one fiber to another over a path. And this always induces symplectomorphisms between the smooth fibers. So almost by definition, we will call a fiber singular if this doesn't happen. This can happen either if it's actually singular, or if there are also accidents, I would say, hiding in the topology at infinity, places where the parallel transport diverges. But excluding these bad scenarios, if I transport a Lagrangian submanifold inside a smooth fiber over a path, I will get a fibered Lagrangian submanifold in the total space that projects to this path. And in fact, every fibered Lagrangian is of this form. So now we'll declare a Lagrangian to be a vanishing cycle for a path that goes from a smooth fiber all the way to a singular fiber if the parallel transport completely collapses this Lagrangian submanifold of a smooth fiber to critical points of the fibration. And then the fibered Lagrangian is called a thimble. I think that terminology was probably introduced by Seidel, maybe by Donaldson before him, coming from the motivation of a case of Lefschetz fibrations that was historically the first one studied. All right. So the prototypical example of this, the one that was brought to the attention of symplectic geometers by the work of Donaldson and of Seidel in the late 1990s, is that of Lefschetz fibration. So a Lefschetz fibration in the language here is the case where the critical points of this function W are isolated and non-degenerate. So this behaves like a complex Morse function. There's a local model that looks like just the sum of the squares of the coordinates on the complex plane. Sorry, on a complex vector space. So a quick calculation, just looking at what does the equation sum of the I squared equals 0 in C to the n looks like, tells us that the singular fibers have what's called ordinary double point singularities. So isolated critical points where, in fact, you can check that the singular fiber is obtained from the smooth one by collapsing a vanishing cycle, which is a Lagrangian sphere. And so you can obtain interesting Lagrangians in the total space of a Lefschetz fibration by parallel transporting the vanishing cycle over a path in the base, the so-called Lefschetz thimbles. And Seidel's work from about 20 years ago shows that the Fukaya category of a Lefschetz fibration is generated by an exceptional collection of Lefschetz thimbles. So you take for each critical point, you take a collection of paths connecting those to a base point or to infinity in our setup will be like more towards infinity. And this produces Lagrangian disks in the total space, which generate the Fukaya category. But the main examples I want to get to show how the subject has evolved since then are things that are not Lefschetz fibrations. In particular, we don't want to assume that the critical locus is isolated or even compact. One of my favorite examples is C cubed equipped with the function Z1 times Z2 times Z3 with, well, a minus sign that's there for some reason. This is actually the mirror to a pair of pants. So it's an important building block for further considerations. So anyway, the geometry of a map from C cubed to C given by the product of the coordinates, while the smooth fibers look like C star squared, the singular fiber over 0 is the union of the three coordinate planes. And so this is singular along the three coordinate axes. And this is a non-compact critical locus with, moreover, it's more spot away from the origin, but at the origin it has a degenerate singularity. What's even slightly more counterintuitive is I may want to allow critical points at infinity. For example, so this one is mirror to the pair of pants, for those of you who kind of want to know where do these spaces come from. This one is actually the mirror of just C squared. This is looking at C star squared with just the sum of the two coordinates. So of course, if you take the derivatives, this has no critical points. But still, the topology of the fibers change, because if I set Z1 plus Z2 equals a non-zero constant, this will look like a pair of pants. While Z1 plus Z2 equals 0 is just a cylinder. Remember, we're working in C star squared, so Z1 and Z2 are not allowed to be 0. And so what changes in the topology is that an arc on a pair of pants connecting two of the punctures shrinks to a point, and the two punctures merge when we get to the 0 fiber. And so in that sense, I would say this arc on the pair of pants is a vanishing cycle, and the Lefschetz thimble corresponding to the real positive axis is in fact the real positive part of C star squared. And this is indeed the most interesting Lagrangian to look at in C star squared. It generates the Fukaya category of this thing. Sorry, it generates the wrapped Fukaya category for, well, same thing here. Never mind. Okay, so enough talking about Fukaya categories that I'm not even, I'm not going to have time to give you a complete definition. I'm not sure I know a good complete definition, but I should at least give you a hint of what this is supposed to be about. So the objects of a Fukaya category are always Lagrangian submanifolds of some kind with extra data and some technical assumptions on them. So in this case, we will want Lagrangians that are what I would call admissible, which means, well, they're properly embedded or immersed in a way that doesn't go to infinity in the wrong places. So the minimum requirement is to ask that they don't go towards the minus infinity end of the fibration. So remember, before I had told you, well, maybe I want fibered Lagrangians that go to kind of towards plus infinity. I can relax that, but what I want to make sure of is that I avoid a region near minus infinity. There need to be some reasonable conditions on how these Lagrangians will behave, just by, to make sure that there's no problems with understanding holomorphic curves with boundaries on these Lagrangians. We're working in a non-compact manifold. We want to make sure that holomorphic disks cannot escape to infinity. So there's a general convexity requirement on the ambient total space, but there's also conditions on the Lagrangians to ensure maximum principles or energy estimates or things like that. Also, we know that if a Lagrangian submanifold bounds holomorphic disks just on its own, as opposed to, so this, if I have a Lagrangian and it bounds a holomorphic disk, that is generally bad for Lagrangian Floer theory. It makes the Floer differential potentially not square to 0. And there's mechanisms algebraically for canceling those, but the simplest thing to do is to assume that the Lagrangians on their own do not bound holomorphic disks, or that we can cancel them somehow. And then once you have that, then you have a pair of Lagrangians. You can associate Floer homology, which studies their intersections, but also has a differential counting holomorphic disks bounded now by the two Lagrangians together, connecting intersection points. And for this to satisfy d squared equals 0, you need some cancellation results about disks. So that's why I'm putting this condition. And then there's also a condition about having spin structures, local systems, gradings, things that you need basically to be able to count disks with signs, with weights, with interesting coefficients, and have potentially a grading on your category if you have the idea that you will want to compare this with coherent sheaves on some mirror space. So anyway, good enough Lagrangians that go more to east infinity than to west infinity. And then when we study their intersections, so the morphisms are given by Lagrangian Floer complexes. This is just some vector space generated by intersection points of the Lagrangians. But in this non-compact setting, we need to agree on a relative position at infinity. And so the rough idea of what you should do is that if you want, before intersecting two Lagrangians with ends towards plus infinity, you should push one of them so that its ends lie above the ends of the other, or maybe I should say counterclockwise from the ends of the other. And so when we study the intersections of L and L prime, we should intersect L and L prime after pushing L by a positive Hamiltonian isotopy, which the simple basic requirement is that on all the ends of L, we should move them so that the argument of W increases. Or if you want, they go counterclockwise in the base, but we don't want to go all the way around and around and around. You could keep wrapping. This gives what's called the wrapped Fukaya category. This is not quite what we want. We do not want to push past the stop at minus infinity. But if we have fiber-wise non-compact Lagrangians, then within the fibers of this fibration, we do want to turn on wrapping and push things around and around at infinity. So that's the general principle or wish list. And then there's many different implementations of that. So historically, the first one that came in the work of Seidel just assumes that you can look at fibered Lagrangians, which are fiber-wise proper, fiber-wise compact. Okay, so fiber-wise proper, I just mean the projection map on the Lagrangian is proper, which means really it's a fibered Lagrangian obtained by parallel transport of a compact Lagrangian in the fiber. So for example, the thimbles in Lefschetz fibrations do that. So then the kind of perturbation I want is very easy to explain. I take a path over which my Lagrangian fibers, I just push it in the counterclockwise direction, and that's it. That's my L sub t. And so before intersecting Lagrangians, I just push them counterclockwise in the base and redraw the fibered Lagrangian above by redoing the parallel transport. Or there's, you can also phrase this as a Hamiltonian flow on the total space, of course. So for things like Lefschetz fibrations, or generally if a fibration is locally trivial at infinity, so if there's no failure of compactness in the critical locus, then this definition is actually quite good. It's sufficient to consider fiber-wise compact objects. But maybe one drawback it has computationally is that it forces you to study the singularity theory of W in a way that's good in some cases and not optimal in some other cases. So there's also a more refined viewpoint that also allows for fiber-wise non-compact Lagrangians that just says, well, let's just look at Lagrangian submanifolds that can go to infinity in certain directions and not in others. And so the language that has emerged for this is the notion of partially wrapped Fukaya category, or more recently, of sectors. So this is kind of a framework that gradually arose. I think first, maybe one of the first instances is Zach Sullivan's thesis, but then after that, Ganatra, Pardon, and Shende came up with this notion of sectors, which really clarifies everything that's happening. So a sector is a symplectic manifold that has some non-compact ends at infinity, but it also has a boundary at finite distance. And that boundary at finite distance is the stop. It's where Lagrangians are not allowed to go to, And then you can talk about wrapped Floer theory of a sector, which pushes Lagrangians in their non-compact ends at infinity, but without ever getting into this other boundary part, the stop. So technically, this is set up with Lagrangians that are conical at infinity. This is extremely versatile. It has wonderful gluing properties and functorial behavior in lots of ways, but it's not really consistent with the fibration in general, unless you take great care or put some very strong assumptions on the geometry. The kinds of conical Lagrangians that appear in this theory are not fibered at infinity. So for computations, you have to make a choice between either you will use the sector viewpoint or you will use the fibration viewpoint. It's not so easy to convert between the two. Maybe it will become easier with work in progress by various people, but right now you kind of have to choose your camp. And then the third viewpoint, which is probably the more ad hoc and less developed one, but it's the one that gets to the results I want to explain. So that's the one I will insist on and inflict on you, is currently called monomial admissibility, but that's probably because so far it's only been developed in cases where the total space is toric. And so there I'm thinking of monomial functions on a toric manifold. But in principle, this should have generalizations. So the idea here is to control the behavior of Lagrangians by having a certain collection of distinguished holomorphic functions, say if we're in a complex world. And for example, this might be toric monomials, but together define a proper map into some vector space. So there's enough such things to control every direction at infinity. And for each of these functions z to the nu, will associate an open subset u sub nu, such that these things altogether cover infinity. So for example, and I want u sub nu to contain the points where this z to the nu is the largest of these functions in a suitable sense. There's a lot of flexibility in the definition. I don't want to kind of give all of it. But for example, you should imagine u sub nu might be the set of points where z to the nu is much larger than 1, or where it's larger than the others, or that sort of thing. And now admissibility is the requirement that the argument of z to the nu on our given Lagrangian is locally constant at infinity in the part that's that's in the region u sub nu. So in each region u sub nu, we partition infinity in our space into various directions, and in each direction, we control some of these monomials. So one example of this is in a vector space, you want to require that maybe the largest of the complex coordinates on your Lagrangian are real positive at infinity. And you only require this of the largest of your coordinates and not of the smaller ones. This is I'm going to give you an explicit example soon in a couple of slides. I just want to kind of front load the definitions and then we can have fun with pictures. I forgot to say, sorry, this constant, of course, should not be real negative. So the argument cannot be pi. And then the Hamiltonian perturbations we'll use for Floer theory will be by increasing the values of all of these arguments at infinity. So what this allows us to do, you can ask, why am I kind of trying to break things into various functions and having this abstract setup? The point is, very often geometrically, this function W in a Landau-Ginzburg model comes as a sum of terms. And I will just focus on the case of a sum of two terms for now. So people who work in the language of sectors are completely used to that because they think of a fiber of W only as something that will be used to produce then a topological skeleton by decomposing the fiber of W using, for example, tropical geometry. So you want to kind of separate in the fiber the regions where the various terms of W dominate. And so what this does is it kind of builds it into the definition of the Fukaya category. So if I think that W is built from a main, what I will call a main term and an auxiliary term, what that means is really I'm decomposing the fiber of W into two components. Instead of saying, hey, I want to look at where W becomes large, say real positive if I want to know where my Lagrangians go, or real negative for the forbidden part. I can decompose that into, there's two ways that W can be large positive, which is either the first term, W0, is large, or the second term as well. And so what this allows me to do is consider, in fact, the geometry of a projection given by W0, but on which the fibers themselves still carry this auxiliary vibration. So what it means is I'm actually considering Landau-Ginzburg models whose fibers are themselves Landau-Ginzburg models. So why would I want to do that? Well, because I can is one option, but maybe a more reasonable thing is, as you'll see on examples, in mirror symmetry for non-Calabi-Yau manifolds, really, Calabi-Yaus always lurk behind. Like the total space of the Landau-Ginzburg model is mirrored to some open Calabi-Yau related to your non-Calabi-Yau space. The fiber is itself a Calabi-Yau that's also geometrically related. So you can do, in this framework, geometry of pairs consisting of a non-Calabi-Yau space and some Calabi-Yau within it or around it. Well, what if you want to relax the Calabi-Yau condition on the second thing? That means that the fiber now needs to carry its own potential, so that its mirror is non-Calabi-Yau. So there's a compatibility requirement, of course, to be able to do that. And I just wanted to point out that I expect this construction of monomial admissibility is equivalent to the others and can be done outside the toric case, but I don't really know that for sure for now. That's, this hasn't been developed outside the toric setting. Anyway, so let's restart now on a clean basis with actually the definition and then a calculation. So the fiber-wise Fukaya category of, say, a toric manifold equipped with a monomial W0 plus extra terms WF, which are again going to be maybe some sums of toric monomials, but I will think of as being auxiliary. So the objects of this category are properly embedded Lagrangians, unobstructed, and so on. And admissibility now is a requirement that if I project my Lagrangian under the main term W0, then whenever W0 is large, its argument will be locally constant. So my Lagrangian projects to a union of radial arcs in the complex plane, and this goes just to the right half plane. I just made my angles be, say, between minus pi over 2 and pi over 2. And of course, inside a compact subset, it could be doing whatever it wants. And moreover, inside each fiber of W0, these are again toric manifolds, just because we have a toric map, we have a collection of auxiliary toric monomials, the terms, including the terms that show up in WF, with respect to which we impose now conditions on the arguments. We require that there's a collection of toric monomials, including all those that appear in WF, whose argument is locally constant at infinity in the fiber, and really locally constant could be 0 in this case. Or you could do, some similar conditions to what I had there. So where does this get us? Well, once we set this up, we can take these admissible. Oh, sorry, one thing I should have said. So when I explain it this way, W0 plays a completely different role from the other terms. And that's the viewpoint I want to use in the rest of the talk, that there is one main projection W0, and fiber-wise, my Lagrangians are also admissible with respect to this auxiliary term WF on the fibers of W0. Monomial admissibility actually you can treat all of the monomials that appear symmetrically, but I will single out one projection. All right. So now you can take a flow on a Lagrangian by a Hamiltonian isotopy, preserving admissibility, which increases the values of the arguments. So basically you rotate all of these monomials at infinity without crossing pi for the terms that appear in W, And for any remaining terms that you can actually push around, you will allow wrapping at infinity. So this is why I'm calling this fiber-wise wrapped. The directions in which there is no term in W are allowed to rotate around and around. So here's an example, because this is all very abstract. So let's look at C cubed with the product of the coordinates. So this is again a mirror to a pair of pants, specifically a pair of pants viewed as a hypersurface in C star squared. This will be relevant pretty soon. So what's the geometry? I want to look at one particular Lagrangian. My favorite admissible Lagrangian is obtained by parallel transporting along a U-shaped arc a Lagrangian inside the smooth fiber. So L0 lives over a U-shaped arc that goes around the origin. And what it looks like fiber-wise, well, the main fiber, so the smooth fibers of this map are just C star squared. And so inside C star squared, I want to take the real positive locus. I see there's a raised hand. Can I help with the question?
Sorry, no question.
Oh, okay. Thanks. All right. So, all right. So, yes. Okay. So we parallel transport R plus squared around a U shape, and then we are going to intersect that. This is my favorite object, and I want to study its endomorphisms. And so what I need to do is push the U shape slightly in the positive direction in the base, not going, so it's actually enough to get both legs of the U to cross each other, basically. This is already the good final position for what to do. And then inside the fiber C star squared, in this case, sorry, maybe I should have said, in this case, there's no auxiliary term, WF. I'm going to bring it up in a couple slides. For now, there's just W0. So fiber-wise, I just want to do wrapped Floer homology in C star squared. This picture is not very instructive. What I mean to draw is, in C star, R plus looks like a ray going through a cylinder, and wrapped Floer homology just perturbs this by a Hamiltonian that pushes it around infinitely many times. So there will be infinitely many intersections. And these actually, the ring structure on that is going to be a ring of Laurent polynomials. And so this is the statement that the real positive part of C star is mirror to the structure sheaf of C star, whose regular functions are Laurent polynomials in one variable. So here you should imagine the same thing in two variables. You actually have Z squared worth of intersections upon pushing things around. And the algebraic structure you would see inside C star squared is Laurent polynomials in two variables. So now, if we go back to the total space, well, the U-shaped Lagrangian and its perturbation intersect in two different fibers. So here we have a wrapped Floer homology of R plus squared and C star squared. And here we have, well, the same thing up to the monodromy of a fibration around the origin, which essentially doesn't do very much in light of this big wrapping. It's a little bit of wrapping by basically one turn in a certain sense, in certain directions. But anyway, these are all things where you can express the arguments of a complex coordinate Zi as functions of a log norms. These are sections over the log map. And of course, admissibility is the requirement that the argument of each coordinate Zi is 0. Each coordinate is real positive, where it's much larger than the smallest of all of them. So in fact, the requirement I put is the smallest coordinates, or those that are tied for smallest, have argument that can be anything, but the ones that are large need to be real positive. And now the wrapping changes this 0 to increase it to instead some constant t, and we take t going to infinity. And so this is why we get more and more and more intersections as things spin around and around. So now a calculation of the endomorphisms of this object tell us that, well, we have the intersections in the fiber over -1. And that was my reference point. And these just look like the wrapped Floer complex inside the fiber. So I've mentioned before, this is a Laurent polynomial ring in 2 coordinates. And in fact, the ring structure on that is, this is a subring, and the ring structure is that as well. And then there's another set of intersections in this fiber whose homological degree is -1. So I'm being told that this should be shifted by 1, so that it's in degree -1. Is that true? Well, something. Anyway, it's in degree -1 is what I mean by this notation. And it's also basically a copy of the same thing, Laurent polynomials in 2 variables. But that one now, algebraically, is as a module over this part here, which is a subring. And there's a Floer differential, which counts holomorphic disks. And the disks of interest here project to this region, connecting the 2 fibers. So the Floer differential goes from this piece to that piece, and a calculation shows explicitly that it's multiplication by 1 plus x1 plus x2, which is the defining equation of my pair of pens. And I should say this is joint work with Abu Said. So at the end of the day, the Floer cohomology is isomorphic, in fact, as a ring to, well, this map is injective, and so it's the co-kernel that comes up. It's the quotient of Laurent polynomials in 2 variables by the ideal generated by 1 plus x1 plus x2. And this is exactly the ring of regular functions on this pair of pens in the algebraic sense, which is why I'm only looking at Laurent polynomials, not all holomorphic functions. Okay, and this is exactly what homological mirror symmetry is about, to say that the A model, Landau-Ginzburg model, so the symplectic geometry of this Landau-Ginzburg model matches with the algebraic geometry of a pair of pens, is the statement, in homological mirror symmetry, is the statement that the derived category of coherent sheaves of a pair of pens is equivalent to the Fukaya category of the Landau-Ginzburg model. So of course, I mean, I've only considered one object. You need to check that this object actually generates the Fukaya category. And you can do a similar argument for general hypersurfaces in C star to the n. There's a similar construction of toric mirrors, and at the end of the day, you get Laurent polynomials, mod and ideal, and that again matches with functions on the hypersurface. Okay, so now I'm going to bring in this auxiliary potential WF that I wanted to tell you about, because the point of all these technicalities at the beginning. So let me first tell you, I'm not even going to go through the details of this. If we have a, where do these like mirrors of hypersurfaces work? Because what I want to get to is mirrors of hypersurfaces in toric varieties. So if I have a hypersurface in C star to the n, or more accurately, I should be working over a non-Archimedean field, but let's not worry about that. Defined by some Laurent polynomial in which I make the coefficients degenerate. So this is where non-Archimedean is actually better, but I can think of those as complex numbers degenerating to 0. Then this might have a compactification or a partial compactification to a hypersurface in a toric variety, which is in fact now f, it's given as a Laurent polynomial on the open stratum of my toric variety, but it extends to a section of a certain line bundle, the line bundle on the toric variety V, whose associated polytope is the convex hull of the exponents that appear in this Laurent polynomial. So I'm just thinking of hypersurfaces very explicitly as defined by equations which look like Laurent polynomials in the open stratum in affine coordinates. So then there's a recipe to find a mirror, which I think originates in Hori and Waffa, and on the math side there's work of Patrick Clark, of Chan, Lau, and Lung, Gross, Kaczarkov, Rudat, Abu Zaid, myself, and Kaczarkov. Anyway, but at the end of the day, the mirror is a toric Kähler-Calabi-Yau variety whose moment polytope is determined by basically the coefficients of this Laurent polynomial. And then it needs to be equipped with a superpotential where there's a main term that's always there, and then there's extra terms that appear for each toric divisor. So for example, if I look at the pair of points 1 plus x1 plus x2 equals 0, the tropicalization of this equation is max of 0, first variable, second variable. The domains of linearity of that are, well, these three regions in the plane, and then drawing a polytope out of this, what lives over the graph of this piecewise linear function, you get a mirror which is c cubed, and the function that you always want on that is going to be the product of the coordinates. Now, if I compactify my pair of points to a line in P2, so in homogeneous coordinates now, x0 plus x1 plus x2 equals 0, which adds in basically 3 points at infinity. Well, not all at infinity, but well, I guess they are, whatever. Along the coordinate axis of P2 is what I should have said. Then the effect on the mirror is to add these three terms of the potential that kind of correspond to these directions of compactification. So that's just a recipe. I mean, it's justified by, for example, the Strominger-Yau-Zaslow construction of mirrors in the non-Calabi-Yau setting or things like that. But it's just a construction. So what happens to our, let's check now homological mirror symmetry for this example, which of course is the, it's not hard to study mirror symmetry for P1. It's one of the easiest examples. I'm just doing it here as a placeholder for really any hypersurface in a toric Fano variety. So let's restart on our C cubed with product of coordinates, but let's add to that now these extra terms. So the rule we'll use is we'll stick to, in fact, the main projection W0, this term, as before, but now we'll declare that the fibers of it, these C star squares, themselves carry WF. And so people in the field know that C star squared with this function is in fact the mirror to P2. And so that's kind of a structural feature that's interesting here. The fiber of W0 equipped with the extra terms is the mirror to this ambient toric variety, whereas without the extra terms, C star to the n was the mirror to the open stratum. So adding the extra terms fiber-wise is mirror to compactifying the ambient space. Okay, so as before, we start with a Lagrangian that's just like, say, R plus squared, or now because we have fiber-wise stops, we need to consider more copies of L0, also things that I will call LK, that twist K times around. So if I were to take a picture for a cylinder, one dimension lower, I would say L0 looks like this, and L1 looks like this, and so on. LK twists K times around the cylinder. So the reason that they're now not the same is because of these terms that put a stop. That means, when I'm not going to push my Lagrangians around in the fiber anymore. So L0 and L1 are not the same thing. So anyway, I can repeat my calculation, and the main change from before is that I no longer wrap completely within the C star squared fibers. Instead, I respect the extra stops put in by this additional potential. And so now, what that does for me is, the calculation is still almost like before, except in here, if I want to look at homs from L0 to LK, I will just leave those things alone, and I will see, in fact, intersections only up to K terms in a suitable sense. Remember, there's more dimensions than I can draw. So let's say these are Laurent polynomials in two variables, which in fact correspond to sections of O of K on P2. So there are things whose homogenization has degree K. And now the monodromy around the origin starts to have a slightly more interesting shape to it, because it turns out that it bends the Lagrangians in the same way as the wrapping, but it does so exactly by one turn. And so in fact, the image of LK under the monodromy looks like LK minus 1. So the story is the monodromy around the origin is, in this case, wrap once. It's a mirror to tensoring by O of 1. In general, for a general hypersurface, it would correspond to twisting by the defining equation, sorry, by the defining line bundle of that hypersurface. And now my Floer differential, counting holomorphic disks that project, that connect those two fibers, is again going to be a connecting map that's multiplication by the defining equation of H. And so at the end of the day, I will still end up with indeed this kind of co-kernel. If K is positive, I end up with a co-kernel of this multiplication map, which will be sections of O of K on P2, homogeneous degree K polynomials, mod the ideal generated by that. And that's exactly sections of a restriction of that bundle to the hypersurface. And so using this, you can prove, in fact, a large chunk of homological mirror symmetry for arbitrary hypersurfaces in toric varieties. And of course, the interesting case is not things like P1, it's things of general type, like higher genus Riemann surfaces, or things of higher dimension with... Anyway, the general type case is where you need the power of this kind of method. So I want to kind of end the talk on a note that explains what's the structural properties going on here. Because, you could say, well, that's a calculation, so what? Why should we care? And of course, maybe, if you care about homological mirror symmetry, you like that this gives a proof of homological mirror symmetry in a rather general setup. But on a symplectic geometric structural note, the interesting thing here is that the Fukaya category of a Landau-Ginzburg model and that of its fiber, which now may be itself a Landau-Ginzburg model, are related by a pair of functors called these days cap and cup. So the cup functor goes from the fiber to the total space, and it's the operation I did on these Lagrangians in the fibers to construct my favorite example for the pair of pants. It takes a Lagrangian in the fiber and moves it around a U-shaped arc, and that produces an admissible Lagrangian in the total space, what I call cap L. Cap, in the opposite direction, basically asks, given a Lagrangian in the total space, what are its ends at plus infinity? And so if you have something that fibers at infinity over a single arc, it's really literally that end. If it has several ends, really what you get is a twisted complex built from the various ends of your non-complex Lagrangian. So these two functors actually fit in what's called a spherical functor, which is a large piece of machinery binding together two functors and a pair of exact triangles and natural transformations. So I'm just going to dazzle you with my newly learned homological algebra. This is not something I'm at ease with, actually, but I think what I want to kind of communicate is if I can do this, then so can you. So the statement is there's exact triangles of functors. So the one that's most interesting to me is on the fiber. The claim is I can look at Lagrangians in the fiber. I can look at their image under the monodromy. Or what I can do is take a Lagrangian in the fiber, first move it around a U-shape by cup, then ask what are the ends of this thing by cap. Well, the answer is the ends will be the original Lagrangian and its image under the monodromy. And in fact, it's not just that. What you get is actually a mapping cone between those, where the mapping cone is given by a natural transformation of functors, which just means for every object L, an element of a Floer complex between these two. And what this element is exactly this count of holomorphic disks bounded by a fish-shaped parallel transport like this. And so this structure is extremely rich. I will not get into the details. There's another one in the opposite direction, an exact triangle of functors on the total space coming from another related construction. Why is this useful? Should end soon. Well, this is useful because it gives proofs of homological mirror symmetry and of its functoriality in different settings. Let me just reveal the whole thing. So this is the setting I was explaining before, but there's another easier setting, maybe more classical setting for what I would call log Fano varieties. So maybe I should start there. If I have a Fano variety X, together with a divisor, so a a hypersurface D0, and I assume D0 is less than the first Chern class, in the sense that I can add another effective divisor D prime to get to the first Chern class, or if you want the anti-canonical. Then, so for example, this could be Cpn relative to a hypersurface of degree at most n. Then I can build a mirror to the ambient space X, which is going to be a Landau-Ginzburg model Y, whose potential has two terms, and some of those terms correspond to the divisor D0, some correspond to the divisor D prime, in such a way that the fiber is mirrored to D0. And so in this way, my two categories, by mirror symmetry separately for X and for D0, match with, I don't know why I wrote perfect complexes. I mean, I know it's for a singular case, but anyway, you can just think of category of coherent sheaves of X and of D0 in such a way that the functors back and forth correspond to the inclusion and restriction of sheaves between a hypersurface and the ambient space. So for example, in mirror symmetry for CP2, the fiber of this whole thing at once is a free-punctured torus. And this is mirror to the cubic, singular cubic in P2 given by just the union of the coordinate axes. But you could instead split off part of this and restrict, for example, to the level of just Z1 plus Z2, which is a pair of pants, and add in a stop, I mean, coming from this extra term. And what you would get is mirror symmetry now for a smaller divisor in P2, which is just, say, 2 coordinate lines instead of 3. In the setup of the previous slide, for a hypersurface in a toric variety, similarly, what happens is the fiber is mirrored to the ambient toric variety. And the total space now is mirrored to the hypersurface. And again, cap and cup correspond to inclusion and restriction. And so, in fact, the calculation I gave above can be understood in this language. So maybe I should just end with this explanation here. The calculation I did for mirrors of hypersurfaces corresponds to, well, I was calculating Floer theory for a pair of U-shaped Lagrangians. Adjunction of functors means I can move the cap to the other side and put a instead I get the Homs in the fiber between one Lagrangian and cap cup of the other, which is the cone of a copy of 2 copies of it, one perturbed by the monodromy. This is what I had. Right? I reduced the calculation to 2 sets of intersections in the fibers and a connecting map, which is counting holomorphic sections of a fibration. And homological mirror symmetry is proved by matching this with inclusion restriction. When you want to consider Homs of sheaves on a hypersurface, and those sheaves are restricted from the ambient space, you can move the calculation to the ambient space by adjunction and resolve basically the sheaves supported on the hypersurface using the defining equation. Okay, I think I'm at the end of my time, maybe even more, so I should absolutely stop here. But thank you for your attention and happy to take questions.
Well, let's all thank Denis. And questions? And whatever. So maybe I will start with a very basic question. I don't know why it's called Landau-Ginzburg model. Is there
that's a good question, but that would be probably best addressed at a physicist. I think, I mean, by now in math, this is just the language for spaces equipped with functions. But I believe the story is, in mirror symmetry, the usual Calabi-Yau setting is meant to be a duality between topological twists of sigma models. Anyway, models whose main field is a map from a Riemann surface to a target space. And the energy basically has to do with the energy of the map. And so sorry, my language is all wrong. I'm not a physicist, so I can't really even fake it. But something like that. Okay, and now instead, I believe, so Landau-Ginzburg models are a class of theories where instead of having just a target space, you have a target space with a potential, or rather it's called a superpotential, and the functional that you consider includes not just the energy of a map, but also a term that has to do with the norm squared of a gradient of W. So you have terms that involve kind of this kind of thing. And what that does, the goal of that is kind of to, I mean, whatever, the classical states correspond to the critical points of W. Anyway, so this is a class of physical theories that I don't really know its whole history and the context, but basically what happens here is this shows up as a modification of the sigma models of mirror symmetry for Calabi-Yau's to insert these superpotentials into the story. For mathematicians, the effect of that is to allow categories that are not Calabi-Yau. Maybe I should have said this earlier. In usual Lagrangian Floer theory, you always have a duality between intersections. You know, if you intersect a Lagrangian A with a Lagrangian B or B with A, you get the same answer up to some dualization that comes from the conventions. But for non-compact Lagrangians and this kind of directed way of pushing them around, you obtain answers that are not symmetric. In the context of homological mirror symmetry, this is important because basically this duality reflects Serre duality. In a Calabi-Yau, indeed, two sheaves, XEF and XFE are just dual to each other on the nose with a grading change. But in general, Serre duality tells us there's a twist by the canonical bundle. And so the canonical bundle here comes realized as the monodromy of this vibration. I'm sorry, that was a non-answer to your question because this has nothing to do with Landau-Ginzburg model in itself. But I think the answer is it's called that way because that's how physicists think of these theories. Oh, Greg Moore has a raised hand and might actually know the answer to this.
Yes, please go ahead, Greg Moore.
No, what you said was just fine, but it leads into a question I had.
Okay.
It's terrible feedback. So the Landau theory is well defined, and the gradient of W is well defined, and that W is multi-valued. And,
okay.
And I was wondering how much of your, from your point of view, you've developed where W is not single valued, but its differential is well defined.
So I think the answer to that is there's probably a way to do things like that. What I would be tempted to do in such a setting is declare, well, you know, maybe first of all, what you have, I mean, I can't really picture it right now in my mind, but maybe you have a vibration over a base that's something different, like might be, for example, if it's just singly periodic, it's a vibration over maybe a cylinder or something. And then I can still put stops, you know, declare that, okay, I will like my Lagrangians to go, say, to this end of a cylinder and not to that end, for example. Or, you know, I'm not sure exactly what I would do, but there's various things like that I can try to do. Another comment is in the language of sectors, we don't even need a projection map or a W. What we need is just to agree on a subset of infinity of our manifold where W, which corresponds to the minus infinity part, that's the stop, that's just where the Lagrangians shouldn't be allowed to go. So in the language of, sorry, I shouldn't be drawing it like that, but basically in the language of sectors, Lagrangians can go to infinity in all except a certain set of boundaries. And so I think to define what it means that W is going to minus infinity, I don't necessarily need W to be single valued. So it might depend also on what, you know, if it's multi-valued up to some additive terms, then I think this is still going to make sense.
Exactly what I have right now. W is the sum of terms involving law. Like that.
Yeah, so I think, you know, one would need to think more carefully about the various possible constructions and which ones actually give the correct answer. But I think conceptually, you know, the broader idea that you just want to forbid W from going to infinity in certain directions, so you're kind of going to split the boundary at infinity of your space into two parts, is kind of sufficient. I mean, in the language of sectors, you don't actually care about the critical locus of W anymore or the existence of this function. You just have a symplectic manifold with some behavior at infinity, and the part at infinity is split into two parts, the stop and the rest.
Thank you.
Mm-hmm. Right.
Koshik, please go ahead.
Yeah, I had this question. Is it possible to have non-homogeneous terms in the superpotential at all, or it's always has to be homogeneous?
Oh, that question doesn't even make sense to me, because I am not planning for my total space to be something homogeneous in general. I mean, my examples were kind of simple ones, but for example, the mirror of CP2 relative to a smooth cubic is in fact going to be a rational elliptic fibration, whose fibers are compact elliptic curves. And no, I mean, homogeneity is not, the total space is not even necessarily assumed to be a vector space or anything like that. My example of toric variety today was C cubed, but in fact, if I want, for example, the mirror to a 4-punctured sphere would be in fact the resolved conifold O of -1 plus O of -1 over P1 with a sum of terms.
Okay.
And so that's certainly not going to be, I mean, in some sense, maybe homogeneity gives an extra grading. Maybe, so examples with homogeneity have additional features, extra gradings, extra symmetries that are very interesting to study. But that's not necessary for the setups I wanted to discuss.
Okay, thank you.
Mm-hmm.
So are there further questions? If you have a question and I don't see your hand raised, you can go ahead and then mute yourself and start asking. Well, if not, I will ask one other question. In the Calabi-Yau case, there is a metric version, a metric part where you want the Ricci flat metric. I wonder if in this non-Calabi-Yau mirror symmetry, there is also some special metric that.
So I mean that's that's a really good topic of study, and in the SYZ approach to mirror symmetry, some indeed try to look for special Kähler metrics. Probably the work you want to look at for that is the work of Collins. I think it's Collins. Collins Jacob Len, maybe. So I probably have something wrong there, but anyway, the idea, I mean, what they do is really around SYZ mirror symmetry for non-Calabi-Yau setup, and the way that it's usually done, because that's easier, is to allow the metric to not be special, but still look at special Lagrangians, put in a holomorphic volume form on the complement of divisor representing the first Chern class, and look for special Lagrangian fibrations. And now you're actually in the same setup that you use in the Calabi-Yau case. You have a base of the SYZ fibration, and there's a preferred metric on it. And you could ask the question of, the Monge-Ampère metric, or the Monge-Ampère equations or generalizations of that. And you could try to get to special metrics on pairs on mirror pairs. But it's pretty hard to do in non-trivial examples.
Okay.
Maybe another answer to that also is, once you delete a divisor, you could say, well, I will just treat the complement as an open Calabi-Yau and try to have a Ricci flat metric on that with specified behavior near the divisor. And that's kind of a more obvious thing that comes out of there, but it's not very intrinsic because it depends a lot on the choice of anticanonical divisor to remove.
Okay, thank you.
Mm-hmm.
Further questions? Well, if there aren't any, then we will thank Denis again. And we will resume in an hour and a half, an hour and 24 minutes to be more precise. The room will stay open until there, so you are welcome to stay around and talk to each other if you want. And we will see you in the next talk. Okay, thank you.